2005, number 3. This is a little bit more about linear regression and correlation. When we look at linear modeling, we really try to determine if linearity is appropriate by using one of a few things. Number one, I can look at the scatter plot. I can look at the residual plot. So part A says, is linear model appropriate? Explain your reasoning. What we can do is we can kind of come back over here to what they gave us and look at the results. I could say yes, the scatter plot is linear. There seems to be no curve. A stronger argument would be to look at your residual plot, and you can see that the dots are randomly scattered. There doesn't seem to be any sort of pattern to the dots. It's not curved like this or going up like this. It's just kind of random scattering about your residual value 0, right? When you have a random residual plot, then the linear model is appropriate. So for part A, you could have chosen two routes. I could have said what I said here, where there is no pattern in the residual plot, or I could have said that there is a clear linear pattern in the scatter plot. You had to do one of those two things. You had to say yes, it was appropriate, and then back it up by basing on one of those two situations. Okay, part B, in this example, or in this part of it, it asks us, suppose the fuel commission cost is $25 per unit. Give a point estimate, a single value, for the change in the average cost of fuel per mile for each additional rail car you attach to the train. A few things should stand out here. Number one, it said we want to talk about change in average costs of fuel per mile for each additional rail car. That should sound somewhat familiar to you. In some ways, that's how we talked about average rate of change per something. This is exactly what the slope is, right? So I'd like to know kind of what my linear regression equation is. Let's go ahead. What we're going to do is we're going to go back over to our data output, and you can see they've listed this. It's kind of nice that they've already got it out written for you here. We've got our linear regression equation. If I hadn't seen that, if I hadn't had it written out for me in this example, we could have kind of gone down here that our y-intercept obviously is always the first value in that list, and then our slope is always the second value, right? So this is y-intercept, and this is going to be slope. That's kind of a consistent thing. Always be careful about that. And really, there's three things I want to make sure to really focus on in this example: is the y-intercept, the slope, this value, and of course, at the very bottom we have r squared. These are the three numbers that anytime I'm going to be doing an example like this, those are the ones I want to make sure I can always pick out and I can always use if I need to. Right, so let's go ahead and write out my line of best fit. Let's not do that now. It's going to be fuel equals 10.7 plus 2.15 rail cars. And now, what I'm going to do now is basically use that equation to get out a few things, and then I'm going to talk about the $25. We know that it's 2.15 over 1 is what my slope is, right? So this would be x here and y there. X is rail cars, and my y is the fuel consumption. And so really what I'm going to be looking at here is it asks me if the fuel consumption goes up every $25 for each additional rail car, then I'd like to know how much money is it going to cost me to add on a rail car, right? For each rail car, how much money would I have to go? Well, I would like to know for each rail car that's added to the load, then how much fuel is it going to cost me, right? Because once I figure out how much fuel I need, then I can obviously multiply by 25 to get my total amount of money that it's going to cost me. And it's kind of already what it's already set up. We know that for each additional rail car, we would expect to use 2.15 units of fuel, right, on average. And so what I can do is I can say 25 times 2.15, because this would tell me, well, you're going to use this much fuel for each car. Then if I multiply that together, we're going to get, that's $53.75 per rail car. Right? So we would expect to spend about $53 for each, $53.75 for each additional rail car, right? Per rail car. I'm going to put this on average because it's not an exact value, right? It's a rough estimate. And so I want to make sure that when I'm using numbers like this, I don't ever give you, oh, it's exactly this much. On the question that was on my AP, a lot of you missed a piece on that because you didn't tell me it was an average value, all right? Or it's an approximate, it's an about. You said it's exactly this number. So be careful when you're talking about slope in a line of best fit. You're always talking about estimated values. Okay? Next part, this is probably the easiest part of the whole thing. It says interpret the value of r squared in the context of this problem. We have r squared. That is 96.7%. And if you remember our little script, we can kind of just go right into that. We would say 96.7%. 96.7% of the variation in the fuel consumption can be explained by the number of rail cars. Okay, don't need to do a whole lot of extra there. There's two things I needed to talk about. I could have gotten the correct answer by doing one of two explanations. Talking about 96.7%, that was required. You had to get the right percentage down. And you had to talk about, it was a variation, in the fuel consumption can be explained by the number of cars, or can be explained by the linear regression model. Those two methods, I think this is much closer to what we had done in the past. So make sure you had talked about that. Okay. And the last part, it's going to ask us, would it be reasonable to use the fitted regression equation to predict the fuel consumption for a train on this route if the train had 65 rail cars? And, well, if we look over here, I'd like to know where 65 falls in terms of my data. If I'm looking at rail cars, I'm going to look at my scatter plot because it's already put in order. It goes all the way up to 50. What is it up here? It goes only up to 50. So to go to 65 would be quite a bit farther down the path. I don't have information about this. It would not be appropriate. This is an extrapolation. So we would really kind of define it like this. We would have to say, no, it's not reasonable. No, 65 is not contained within the data set. Extrapolation is not a reasonable endeavor, right? We don't ever want to trust something that we don't have data to fit, right? If we look at our data set here, we know that it goes up to about 50. Go to 65 would be quite a bit outside of my data set. Now this may be true, but I don't have any data to back it up. I don't know that it would be a reasonable assumption to make. Okay, hopefully this was relatively easy for you. There was a few things here that I wanted to make sure to mention. This example, or this problem here, and the one with talking about the slope on average, that was an issue that happened on the previous example we had on my AP. I just wanted to kind of make sure to go over this and talk about it with you. Okay, got any questions? Please let me know.